Hello, everyone. Thanks for having me here. I'm Yingjun Wu, the founder of RisingWave Labs. Today, I will talk about building cost-effective stream processing applications with RisingWave and Apache Pulsar. Well, I will first start with a self-intro and then discuss why we need stream processing and how much cost you need to pay for getting a stream processing. I will further give an introduction to RisingWave and explain why RisingWave may be a good option for stream processing. I will further showcase how easy it is to use Apache Pulsar and RisingWave to build a cost-effective application. So, well, again, I'm Yingjun Wu, and I'm currently running a company called RisingWave Labs. RisingWave Labs is a database company that building RisingWave, a SQL streaming database in the cloud. Parallel to running of this company, I was a software engineer at AWS Redshift and a researcher at IBM Research Armadan. I obtained my PhD from National University of Singapore, majoring in database systems and stream processing systems. So let's talk about some background, right? In the modern digital world, people really need to get the real-time insights. So just to think of the applications like stock market monitoring, inventory management, parcel tracking, web click streams, right? For all these kind of applications, you probably really want to get a fresh results, right? You probably don't really want to say, okay, I just want to see how what the price looked like of the stock market yesterday, right? We really want to know, okay, what was happening over the last probably just 30 seconds, right? And obviously, the fresher the result is, the higher the base value we can get. But the problem here is that how we can generate fresh results, right? Well, if we want to refresh a result every few hours or days, that is the freshness is okay, several hours or days, right? Then conventional batch systems such as Hadoop, such as Spark, such as all kinds of the batch systems may be a good fit. And the reason here is that these batch systems can perform complex queries over large amount of historic data. So basically, if you want to have a, if you want to use a database system like a Hadoop or Spark, what you need to do is that you need to bulk load the data into the database into the system, no matter whether it's Hadoop or whether it's a Spark, right? Bulk load into a system, and then trigger the query every few hours or every several days, so that you can receive the results accordingly. Well, this kind of system work well when processing. I mean, if you do not really care about the freshness, but if our expectation of the data freshness is just a few seconds or probably just minutes, then this kind of batching systems are no longer the right choice. And why? The reason here is that bulk loading and processing data can cause high latency and making it unsuitable to support real-time applications. And then what we can do? Well, the answer is obviously it's stream processing. In a stream processing system, well, it's quite different. The computation model is quite different from the batch systems. A stream processing system can do the event-driven, it actually adopts the event-driven processing model and performs incremental computation instead of full computation. So what it means is that, okay, if you have a chunk of data, right? Every time a new tuple comes in, the stream processing system will update the results for you. But if you're using batch system, you have to upload all this data. You have to ingest all this data into a batch system and then do a bulk processing. So let's talk about the streaming data stack, right? Well, this chart actually shows a pretty classic streaming data stack. Every time a new event comes into the messaging system such as Pulsar, such as Kafka, or such as Kinesis, the event will be buffered in the messenger queue and then be consumed by the downstream stream processing systems. The stream processing system will do some, as I just mentioned, will incremental computation. It will refresh the results for you and deliver the data down to the downstreaming systems. So for example, okay, if a new tuple comes into Pulsar, then what will happen? Well, the underlying streaming systems, well, the downstream, the streaming processing systems in the downstream will process that event, that single event, and trigger the computation and update the results, if there's any, right? Update the results and deliver the results, deliver delta into a downstream delivery systems. So classic stream processing systems include SAMSA, Storm, Flink, and many others. Well, the databases, well, if you talk about databases, there are probably many more choices, such as Redis, such as Cassandra, such as Postgres, and MySQL definitely, right? Well, the streaming data stack shown here actually works. It actually works in many companies, but the problem here is that it can incur high cost. If you check around, what you'll find is that most of the companies are actually probably tech companies who actually can have a group of engineers that can have that manage the system and maintain the system and develop the applications. But maintaining such kind of streaming data stack actually incurs pretty high cost. And why? I can actually explain it from 3 dimensions. The first one is the high maintenance cost. As I mentioned, well, if you want to support such kind of streaming data stack, you will need not just a messenger queue such as Pulsar or Kafka. You also need to have a stream processor, right? Such as Flink. And in addition to that, you also need to have a database system in the downstream to hold the result. And why? Because stream processing systems such as SAMSA, Flink, and Apache Storm do not really store the results. So essentially, if you care about the results, you have to have some system to maintain the result. And that's why you want to have a database system. So yeah, that means that if you want to do stream processing, you have to have both the stream processor and the database system. It can be pretty costly, right? Even if you say that, okay, I do not really maintain a system, I purchase from the cloud vendors, then you have to still purchase 2 different systems, which can be quite expensive. And the number 2 is the development cost. All right, think about the stream processors, right? Okay, now you have Pulsar, and now you also have a downstream delivery system such as Redis or Cassandra, right? And you are trying to develop the applications inside of the stream processors such as SAMSA, Flink, or Apache Storm, right? The problem here is that it will be super difficult for you to validate whether your program is correct or not. And why? Well, because the database, the stream processors do not really store the results. So it does not really own the input, and it also do not really own the output. So to verify the correctness of your application, you actually need to look into your upstream systems and the downstream systems and check, okay, whether the input and output matches, right? Which can be pretty costly. And there are actually several other reasons about that leads to high development cost, and we can mention it later. And the third cost is execution cost. Well, think about the stream processors systems such as Samsung's Starlink Storm. I mean, all of them were built in the big data era, which was 10, 15 years ago. And there at the time, there was no cloud. So what people do is that they do embarrassing parallelism. What it means that it will shard the data streams into different machines, and then every single machine will process the data streams independently. This actually worked great if you have already had a bunch of data. If you have already had a bunch of machines. But the problem here is that if you are in the cloud, then it's not efficient enough, because in the cloud, you can have the remote storage and you can have the EC2, right? Computation node. And these computation resources, all these resources should scale in and out independently and infinitely. Using the conventional big data architecture won't work, because what if the workloads fluctuate? You have no way to scale in and scale out, and which can cause, either the system will crash or you actually pay extra money, right? So in terms of execution, existing stream processing systems are definitely, not very efficient. So how to solve this problem? Well, that's why we have that's why we are developing a system called RisingWave. Well, RisingWave is actually a distributed SQL streaming database. Well, what it means, streaming database system? Well, it's essentially, you can just imagine it like a database system that can process streaming data. So inside of RisingWave, it has its own stream processor. And the stream processor is responsible for processing data streams. After processing, it will deliver data into downstream systems, into downstream storage, which is also maintained by RisingWave. So every time a new tuple comes into a system, RisingWave stream processor will do the computation, update the result, and deliver the result, and all actually reflects the result into its own storage. And users can directly talk to RisingWave by issuing SQL queries and check the result. And that's essentially how RisingWave works. So if we go back to the previous, the streaming data stack, where RisingWave is. Well, essentially, RisingWave can replace both the stream processor and the database system. So instead of maintaining two different types of systems, you only need to have one single database system, that is RisingWave. People can directly talk to RisingWave. Again, well, as mentioned, people can directly talk to RisingWave just as using SQL, Postgres database, and check the result. Then, okay, RisingWave is a database system. Then how do we issue streaming jobs, right? In the old-fashioned streaming systems, you have the streaming concept called streaming jobs, right? In RisingWave, it is a database system. Then how do you issue the streaming jobs? Well, essentially in RisingWave, there's no concept called streaming job. What it has is actually the materials view. Materials view is essentially the key concept in RisingWave. Think about what is materials view. Materials view actually maintains the result for you and make sure that the result is up to date. In RisingWave, in conventional database systems, well, materials view may be stale. The database system may not update a result or may not update a result in materials view frequently. But in RisingWave, materials view is actually triggered and maintained by the stream processor. So if you want to create a so-called streaming job in the conventional streaming processors in RisingWave, the only thing you need to do is to create materials views. So in this example, as shown in this figure, the only thing you need to do is to create a materials view, add CTR as a select statement. And in this way, you can create essentially create a streaming job, and the materialized view will always be updated every time a new tuple comes in. So having materialized view can actually help greatly improve the greatly improve the efficiency. Why? Well, definitely from two dimensions. The first one is the development cost. Well, in the conventional streaming systems, you will probably have to create several independent streaming pipelines, right, or streaming jobs, right? But in RisingWave, you can essentially create a streaming job or materialized view on top of another materialized view and create a materialized view on top of the previous materialized view, right? It's essentially a stacked materialized view. So this means that you can actually reuse the logic, computation logic defined in the previous materialized views, right? Which can be pretty powerful because you do not need to write redundant code. And second thing is that because you can reuse the materialized views, right? The magic here is that you are essentially sharing the computation resources among different materialized views. And these materialized views can do the computation can do part of the computation just once. So that means that it can help you save a lot of computation resource. But in conventional streaming processors, well, I mean, you anyways you need to create different streaming jobs, and every single streaming job needs to, create do the computation independently, which can incur pretty high execution cost. Right? Then let's talk about the storage. Well, RisingWave compared to existing streaming processors, well, it has its own storage. And storage can help serve the concurrent ad hoc queries, which means that if you have multiple users, they can just issue ad hoc queries to query the materials view, and because our materials view host maintains the streaming result, right? The users can always check the latest results reflected in the materials view, right? So which can make your life much easier because you do not really need to maintain two separate systems. One is a streaming processor and another is an independent database system. A good thing I love in RisingWave is that it's fully Postgres compatible. I mean, it's not developed on top of Postgres, but it can talk, and it's well compatible with Postgres. And what it means is that as a user, you can actually talk to RisingWave using PostgreSQL dialect. You do not need to learn different SQL dialects, right? Big data SQL or MySQL SQL. No, you do not need to learn that. You can just use PostgreSQL dialect. And because it's well compatible with Postgres, it also means that as long as a system have integration with Postgres, the system can be integrated with RisingWave. And this means that essentially, if you're a Postgres user, you can just reuse all the database tools you love in RisingWave. Well, let's talk more about the technical depths. Let's talk about more about the technical stuff in RisingWave. Well, as I mentioned, conventional stream processors adopt a coupled computing and storage architecture, meaning that the system essentially shuffles the shards of streams using some hash partitioning mechanisms, right, into different machines, and every single machine will process their own streams, right. Well, in RisingWave, the different thing here that it adopt decoupled computers in storage architecture, which means that the storage will be maintained in the remote storage. The local state will be maintained in the remote storage. So what we will have in the local machine is just some caches. Which means that if the node crashes, no worries, because it's just the caches. You can just reload the cache in some other machine, in several other machines, and reboot the system, right? Reboot just a node, not a system, right? Which is kind of quite efficient. So this brings several benefits. The first one is about the execution. Well, because you can maintain large states in the remote object store, you do not need to maintain let's say 100 EC2 nodes, because that would be very expensive, right? So you can just probably create just 10 EC2 nodes, and every single EC2 node will access the storage in the remote storage, right? But the performance, you do not need to worry about the performance, because we still have the local cache. And in the cloud, we also use the services like EBS to improve the performance, to make sure that, okay, even if the cache misses, we will have some guarantees, performance guarantees. And the second thing is elastic scaling. As I mentioned, because the storage is actually maintained in the remote storage, or the local state is maintained in the remote storage, if the workload fluctuates, you probably really want to scale in and out. And in this case, you do not need to, let's say, migrate states from one machine to the other. Right? The only thing you need to do is to create several other machines, and all the other machines will, the newly created machines will directly fetch the data from the remote storage. And that can make things much easier, right? And then what about the failure recovery? Well, failure recovery is same as the elastic scaling. If one of the nodes failed, you do not need to worry about that, because we can just instantly create another machine, and you ask that machine to reload the lost cache, just a cache, not a state. Reload the lost cache from the remote object store, and the failure recovery will be done instantly. Well, I've already talked so many things about RisingWave. Then let's talk about, well, how to build cost-effective real-time applications with Apache Pulsar and RisingWave. Well, let's just take the ad monetization example in there, right? So in this example, we have two different streams. One is the ad impression stream, and the other one is the ad click stream. So imagine that these two streams are maintained in the messenger queue, like in Pulsar, right? How to connect RisingWave to Pulsar? Well, the only thing you need to do in RisingWave is to write a SQL code and to create a source, add impression with, and set a connector to Pulsar. That's it. Tell me the IP address and tell me a port, and then you can create you can link RisingWave to Pulsar. So after connecting RisingWave to Pulsar, I mean, and adopt right. And the next thing is to create a multi-phase view. Again, the only thing you need to do to create a streaming job in RisingWave is to use the statement called create multi-phase view. In this example, add CTR as select statement as followed, right? And this can make the streaming job creation pretty simple. You do not need to worry about how to upload a job, your job, right? You do not need to worry about that. The only thing you need to do is to write a SQL statement. And then how about the query statement? Well, sorry, query the result. Again, different from the conventional, the streaming systems, you do not need to maintain a separate. You do not need to maintain a separate, like say, a database system, because RisingWave itself is a database system, which means that it can maintain the result for you. So to query the latest result, the only thing you need to do is to run the SQL query and query the data in the materials view. So that's how RisingWave can be used. All right, let's conclude the talk. So, well, building stream processing applications can be pretty expensive. because of several reasons. Well, first, you have to maintain different systems, right? You have to learn how to develop a system. And you also need to worry about, okay, how much cost it will take, how much execution cost will take, right? And RisingWave is a solution to simplify stream processing. Well, it is a distributed SQL streaming database that can provide both the stream processing and query serving capabilities. It uses the decoupled compute and storage architecture to reduce the cost, and it offers Postgres experience to users. Building stream processing applications with Pulsar and RisingWave can be quite extremely simple and effective. Well, all right, that's all my talk. I'm Yingjun Wu from RisingWave Labs. Well, if you have any problem, if you have any questions regarding how to use RisingWave and Pulsar, just let me know, and I'm here to help. Thanks.